Let us begin. Today, we're going to be talking about some implicit differentiation again. And then we're going to be reviewing for the exam on Friday. We won't get all the way through the practice exam, but Thursday we'll also do some more review. Okay. So before we start, exam on Friday. Make sure you know that. And then that's it. That's all the announcements I have. Okay, so do we have any questions before we get started about anything? No questions? All right, so last time we talked about implicit differentiation. This is going to be a pretty powerful tool for us. Like we saw, it helps us to differentiate functions that are implicitly defined by an equation, okay, involving both x and y, or in general, a dependent variable and an independent variable. Okay, so this is going to help us. So think the standard example is the equation for a circle: x squared plus y squared equals r squared. A circle is clearly very smooth, and it should have a tangent line at every point. So we want to be able to find that tangent line without having to break apart that really nice equation. This is kind of why, this is where this idea of implicit differentiation comes from, okay? And it's just an application of the chain rule. Okay. All right, so let's look at an example of implicit differentiation before we move on to a slightly different but related topic, okay? So we're going to find the equation of the tangent line to the curve described by the equation x squared plus y squared squared is equal to -8 times x squared minus y squared at the point 1 comma square root of 3. Remember, I have to give you a point, the full point in these types of problems, because it's no longer just enough to give you the x value. Because looking at this graph, this is really the graph of this equation here. If I just gave you the point, the x value 1, well, you don't know if I'm talking about that value there or that point there, right? So implicit differentiation problems, especially when you're finding tangent lines, I have to give you a point to plug in, okay? So we're looking at this guy right here, 1 square root of 3. So my final answer is going to be an equation, right? The equation of a line. So what two things do I need for the equation of a line? Slope, m, and what else? A point, exactly. The point is obviously that guy, 1 square root of 3. Slope, yeah, that should be the derivative. Anytime slope comes up now, you should immediately think derivative, specifically dy dx. One question that hasn't come up yet that is valid is, well, if y is defined implicitly as a function of x here, isn't x defined implicitly as a function of y? And the answer is yes. And if we wrote lines as x is equal to some slope times y plus some x-intercept, then we would be interested in dx, or sorry, dy, dx, dy. Then this would be the slope there. But we usually don't write lines that way. We usually write lines y equals mx plus b. And for that, we want dy dx, okay? But it is a perfectly valid question to say, if y is defined implicitly as a function of x here, well, also x is defined implicitly as a function of y. And in fact, they are inverse functions, which we're going to talk today about, okay? So we need dy dx, specifically at the point 1 comma -3. So how am I going to get that? I need the derivative of y with respect to x. Well, this is the only place I have any y's happening, right? So what should I do with that equation?
Rearrange it.
I could rearrange it, but that is going to sort of defeat the purpose of implicit differentiation. I could rearrange it to get y by itself, but in general, that's going to be a really hard problem. It would be really tough to get y by itself here. So instead of rearranging and then differentiating, yeah, the whole idea behind implicit differentiation is sometimes it's hard to get y by itself. So let's just differentiate this whole equation, both sides. And when you do that, you'll still get something that equals, right? So I'm going to differentiate both sides of this. D dx of x squared plus y squared squared. This has to be equal to d dx of -8 times x squared minus y squared. All right. There's not really an easy side and a hard side here. They both have x's and y's happening in them. Someone says, is it a good idea to simplify both sides first? Again, you can, but that's kind of defeating the purpose of implicit differentiation and this really powerful tool that we have in the chain rule. That kind of defeats that purpose a little bit. So it's got to be a case-by-case situation, I'll say that. But in general, I won't expand this first. I'm just going to use the chain rule and go from there. Okay. So the derivative of the left. All right. Well, I need to know, first of all, just what's the derivative of something squared?
Something.
2 times something to the first, right? That's still too big. 2 times something, that's something on the inside to the first. Oops. Erase. So we get 2 times the inside. And then now what do I need to multiply by? So I took the derivative. Nope. I'm not quite done taking the derivative yet. I took the derivative of the outside and I plugged in the inside.
Then you take the derivative of the inside and multiply by the outside.
Yeah, multiplied by the derivative of the outside. Yeah. So yeah, exactly. So I cover it up. Oops. I cover up the inside. I just take the derivative of the outside at the inside, and then multiply by the derivative of the inside. Okay, so the chain rule. So I need to multiply by the derivative of the inside. So what's the derivative of the inside function here? Perfect, 2x plus 2y, and this is a chain rule here. So we actually have the chain rule twice. Oops, 2y dy dx. Okay, so this is actually the chain rule 2 times. Perfect. All right, so that's the derivative of the left. That has to equal the derivative of the right. Well, this -8 is just going to come along for the ride, right? Just a constant. And the derivative of x squared minus y squared is what?
2x minus 2y dy of dx.
Perfect. And again, this just comes from the chain rule because y is implicitly a function of x. Okay. Perfect. So let me do this smaller down there. Okay, so we've got, let me rewrite this with a little more room. 2 times x squared plus y squared times 2x plus 2y dy dx is equal to -8 times 2x minus 2y dy dx. Okay. Now I could plug in straight away my point, right? I mean, I could try and solve for dy dx first. The algebra is going to be a little easier if I plug in my point right away that I care about. Because after you've taken the derivative, you can go ahead and plug in the point. You shouldn't plug in first and then take the derivative, because what would you get if you plugged in a point and then tried to take the derivative? You would get 0. If I plugged in a point, I'd have only numbers, right? Only constants, and I take the derivative, I'd get 0. And that's something that trips people up with these types of problems. You have to take the derivative first, then plug in your point, okay? So I'm plugging in, plug in 1 square root of 3. All right, so when I do that, I'm going to get 2 times 1 squared plus the square root of 3 squared times 2 times 1 plus 2 times the square root of 3 dy dx. This is equal to negative 8 times 2 times 1 minus 2 times the square root of 3 dy dx. Okay. So let's simplify a little bit. This is going to be equal to 2 times 1 plus the square root of 3 squared. Well, square root of 3 squared is just 3, right? So this is going to be 2 times 4 times 2 plus 2 square root of 3 dy dx equals negative 8 times 2 minus 2 square root of 3 dy dx. All right, so this is 8 right here. This is an 8. So I'm going to get 16 plus 16 square root of 3 dy dx equal to negative 16 plus 16 square root of 3 dy dx. And then what happens? Careful. Because I'm going to add that, right? And and it's actually very important that they don't cancel for this example. But what happens with, I've got the same thing involving dy dx on both sides, right? So when I subtract that, that does cancel. And we're left with minus 16 square root of 3 dy dx. We're left with 32 equals 0. What happened? That is clearly nonsense. So what happened here? Yeah, the 16 square root of 3 is canceled. So yeah, I'll add a piece of paper and do that a little more slowly. So we have, I'll erase this. So first of all, when I add 32 or 16 to both sides, I get 32 plus 16 square root of 3 dy dx is equal to 16 square root of 3 dy dx, right? Everybody okay with that? Let me get rid of this. There we go. Okay, so then I have the same quantity here on both sides, right? So when I subtract that off, trying to get dy dx on one side, it actually just goes away completely, okay? And I'm left with 32, because I didn't touch the 32, equals 0. So something seems to be going quite wrong here. So what do we think it is? Yeah.
Well, if you look at the graph.
Ooh, yes. Yeah. Let's look at the graph here. The tangent line is vertical, right? At this point that we care about, the tangent line is vertical. This is why I included the graph here. that tangent line is vertical and its slope is undefined, right? So when you're going through an implicit differentiation problem like this, and you end up with something that looks like 32 equals 0, or you end up with something that's nonsense, that's an indication that maybe the slope is undefined at this point that we're trying to find the tangent line. Okay. Not always. It could also be the function is not smooth there, and it just doesn't have a tangent line at all. Here we do have a tangent line, right? And the tangent line is equal to what? What is this line? X equals 1, exactly. This is just x equals 1 is the tangent line. Okay. So implicit differentiation problems, with an explicit function of y, we would have gotten something like 1 over 0 or something like that. Now with an implicit function of x, we still end up with some nonsense. Because, I mean, another way you can think of this is 32 equals 0 dy dx. You could think of it as like, then you would divide by that 0, right? But we can't divide by 0. So that's what's happening here. If you end up with something that's nonsense like this, you might be looking at a vertical tangent line. Yes?
So how would we, because obviously this is nonsense, and like you can't clearly write an equation, but it's asking for one, so is that the x equals 1?
Yes, x equals 1 is our final answer. X equals 1, that is the tangent line.
Okay.
Yes, excellent question. Any other questions? I did want to show what could go wrong with implicit differentiation. But it's not really anything going wrong. This is really just an indication that we write lines, you know, depending on y and x, and this just doesn't depend on y really. Okay, so all right. Oh, do we have any questions online? It looks like yes. Excellent question. Someone says, could we do point slope form with this? Sort of, but not really. Point slope form depends on a slope being defined. And here our slope is undefined, right? Our slope is, you could think of it as 1 over 0, right? We go up 1, we start at x equals 1, we go up 1, and then over 0. But again, that's 1 divided by 0 is undefined. So this is the only way to write your answer, x equals 1. Okay. Yeah, good question. Any other questions? On an exam, I would not give you a case like this. I would give you something like a point right here, where it does have a well-defined slope, and you can write down the tangent line in point slope form. Okay. All right. So with implicit differentiation, we can use this to find derivatives of inverse functions. Okay. So a reminder, if f of x is a one-to-one function, then its inverse, which we write f inverse of x, this is how we write the inverse function, f inverse of x, is the function such that f of f inverse of x is equal to f inverse of f of x. Both of these are equal to the same thing, and that thing that they equal is just x. So we're going to use this to find derivatives of inverse functions, okay? Specifically, we're going to find the derivative of the function f of x is equal to sine inverse of x. Okay? And by the way, this is, I know it's so annoying that when we write sine squared, that just means take sine, if we write sine squared of x, that just means take sine of x and raise it to the 2. This is the one special case, sine to the -1. That means the inverse sine. We're finding the inverse function. Okay. I know it's so annoying, but I didn't make up the notation. So sine inverse. So y equals sine inverse of x. All this means is, because sine of sine inverse of x is just equal to x, all this really means is x is equal to the sine of y. Okay? To find inverse functions, again, you just swap x and y and then solve for y. So that's really all that's happening here with sine of x. There's no really easy way to do that, so we just come up with this new function named sine inverse of x. Okay? So let's write this out. So if we have f of x, oops, that's wrong. If we have f of x, I'm going to call it y, is f of x, is the inverse sine of x. Then I'm just going to use this fact right here to say that x is equal to the sine of y. Okay? So we still have y is still implicitly a function of x, right? Even though now I don't have y just by itself. This is still an equation involving x and y, and I can, if I want, I can solve for y, but we're going to start here to find dy dx. That's what we want to find here, right? We're trying to find the f prime and y is f of x, okay? So if I use implicit differentiation here, then if I take d dx of both sides, the derivative with respect to x, then that's going to tell me, well, what do I get on the left-hand side? Yeah, on the left-hand side, I'm just going to get 1. On the, oh, sorry, that should be a y there. So on the left-hand side, I'm just getting 1. On the right-hand side, well, the derivative of sine of y with respect to x is what? The outside function is just sine, right? So what's the derivative of sine of something? Cosine, and then at the inside. And then what do I need to multiply this by? Dy dx. Yeah, exactly. I need to multiply by the derivative of the inside. Dy dx. Okay. And so this tells me that the derivative of y with respect to x, which is what we're trying to find, is 1 over cosine of y. Now with this example, I asked in terms of x. We started with a function of x, an explicit function of x. I should give my final answer as an explicit function of x. Okay? So the way I'm going to do this, remember that x is the sine of y. And we're going to use the fact really quick that cosine squared of y plus sine squared y is equal to 1. Okay, everybody remember that? Cosine squared of anything plus sine squared of anything is equal to 1. Okay, but what is sine squared y? What is sine of y? Sine of y is just x, right? So sine squared of y, remember that means sine of y squared. So this is just x squared. Okay, and so that tells me cosine squared y plus x squared is equal to 1. Which then tells me I'm trying to figure out what cosine of y is. So let's get cosine of y by itself in this identity here. So that tells me cosine squared y is equal to 1 minus x squared. Just subtract x squared from both sides. And then, lastly, to get cosine of y by itself, I'm just going to take a square root. So cosine of y is equal to the square root of 1 minus x squared. Okay? And so that tells me that the derivative of y with respect to x as an explicit function of x is 1 over the square root. I'm just replacing cosine now with this, of 1 minus x squared. Okay. So with finding derivatives of inverse functions, there's a little bit more work involved because we do switch to an implicitly defined function of x, but then we need to switch back at the end if we're given an explicit function of x to start with. So finding all the other inverse trig derivatives follows in exactly the same way. Okay? Inverse trig derivatives won't come up a lot in this class, just so you guys know. It is important to see this. It's a cool application. Also, it's important to see this because maybe at the very end of this class, definitely in Calc 2, if anyone's taking Calc 2, you'll need to know this derivative of inverse sine of x. Okay, it's important for certain methods that we're going to use in Calc 2. So, are there any questions about this? Okay. So, one last thing, higher order derivatives with implicit differentiation. Work exactly the same way. The only really small thing that I thought was worth mentioning, where I've been writing f double prime before, if y is equal to f of x, then what we have been writing dy dx, that's just f prime, right? F prime of x. And f double prime, the way we write the second derivative of y with respect to x, and this is really just a notation thing. This isn't a new concept at all. But the notation we use is d, you can say d squared y over dx squared. When I was first learning calculus, this annoyed me so much. What you should think of is what I thought, why isn't it this? Why isn't it that? And the reason is, if you notice before, I've been writing like d dx of stuff equals something. The second derivative is just I'm applying the derivative again. This is the notation we use to say I'm applying the derivative. And so I'm applying this d over dx twice. That's why only the d in the top has a 2. Okay. For math majors, if anyone's going to be a math major, which all of you should be, you're all fantastic at math. I'm genuinely very pleased with how you're all doing. This is what's called an operator. You'll get much more into that in your higher level math classes. Okay. But that's where this notation comes from, right? Second derivative of y with respect to x. All right, so let me get rid of this, delete. All right, so I want to find, with this equation here, x squared plus y squared equals 2, just a circle with radius square root of 2. I want to find the second derivative of y with respect to x. Okay, so the way we're going to do that is first, to find the second derivative, you need to find the first derivative, right? So let's find the first derivative first, and then we'll find the second derivative second. Okay. So to find the first derivative, I'm just going to do what we've always done with implicit differentiation and differentiate both sides. We'll do the easy side first. What's the derivative of 2 with respect to x? 0. All right, now the left-hand side. What's the derivative of x squared plus y squared with respect to x? Well, what's the derivative of x squared with respect to x? 2x. Plus, what's the derivative of y squared with respect to x? Perfect. 2y dy dx. Again, that's just the chain rule, because y is a function of x implicitly. So then we do a little subtraction. I'll subtract 2x from both sides, and I'll get 2y dy dx is equal to negative 2x. And I just divide by 2y with the caveat that y can't be 0, right? So when I do that, I get dy dx is equal to negative 2x over 2y. 2's cancel, and I'm left with negative x over y. Okay, so I have dy dx here. All right, now how do I find the second derivative of y with respect to x? Exactly, yeah, exactly. I'm just differentiating this, right? So I just need the quotient rule. Okay, so the quotient rule, I have a high of x and a low of y. So I'm going to do low d high. So I'm going to get the negative out in front is going to just come along for the ride, right? So I'm going to get low, which is y, d high. What's d high? Derivative of x with respect to x? Just 1, perfect. Minus high x d low. What do I write for that? Perfect. Oh, it's so good. dy dx. Everybody see that? The derivative of y with respect to x? That's just what we've been calling dy dx. Divided by the square of what's below. So divided by y squared. Okay? Technically, you could leave it like this, but what should we do? Almost exactly right. Not solve for it, because we've already solved for it, right? That's what we did in the very first step. So what should I do instead of solving for it? I should plug it in, exactly. I should take what I know dy dx is and plug it in there. Okay, so this is negative y minus x times negative x over y divided by y squared. Okay. So this is negative. The rest of this is just simplification. So negative y plus x squared over y all over y squared. If you wanted to leave it like this, if you were in a time crunch on an exam, I would probably give you full credit for this. But let's go a little bit further. This is negative. I want to get a common denominator in the top. Well, that common denominator is y. I'm going to get negative y squared plus x squared over y all over y squared, right? Which is negative x squared plus y squared divided by y to the third Does everybody see why there's a y to the third in the bottom? Yeah.
So you kind of lost me when you got to the y over y squared. Is that because you're plugging into the negative x over y from the first derivative?
Yeah.
Okay.
Yeah, exactly. Yep. And do we have any questions online? Yes, exactly. Yeah, the way I got to here is, yeah, you flip the bottom. The bottom's really y squared over 1. You flip the bottom and multiply, right? And then who sees the one last, if you saw this on an exam, I would probably give you bonus points. Who sees the one last simplification we can make?
Can't you just like take
What was it? Careful. In order to cancel any y's, I would also have to have y's multiplying there. Okay. So I can't cancel any y's, but whoa, yeah. What's x squared plus y squared? Careful. What did we start with? X squared plus y squared is 2. So if you saw that on an exam, I would scream for joy. So this is just negative x squared plus y squared. That was just, we started with that, and that was 2. Okay? Divided by y cubed. So there's the derivative, the second derivative of y with respect to x. Okay? Questions before we start on the review? That was great. I am genuinely very pleased with you guys. So, all right, so let's get into some exam review. This is a practice test. The way I did this, by the way, is I wrote out what I thought would be a good test as a first draft, and I said this is just a practice test. So the real test is going to be based off of this first draft. There might be a few minor changes and a few small things that are different, but I wrote this intending it to be a first draft of the exam. So take that for, what it is. So problem 1, the definition of the derivative. Use the limit definition of the derivative to find f prime of 2 if f of x is x over 5 minus 5 over x. If I give you a problem like this on the exam, and you just use the power rule, and you don't write any limits, you'll get 0 points. It is perfectly fine to use the power rule to check your answer, to make sure when you do take the limit, you get what you should. That would be fine with me. But if you just write down that f prime of x is 1/5 minus, or really plus 5 over x squared, and then plug in 2, you're going to get 0 points on this problem. Okay? So, how do we actually do this? Let me add a page and then. Well, the limit definition of f prime of 2. Yeah, start with the limit as h approaches 0 of, what's the rest of it? Yes, f of, and for us, we're doing x is 2, right? 2 plus h minus f of 2. And what's this all divided by? H. Yeah, perfect. And remember, this came from the tangent line. We got the slope by looking at secant lines and taking the limit as the change in x got very, very small. Okay? So this is equal to the limit as h goes to 0 of, well, f of 2 plus h. Well, that's 2 plus h divided by 5 minus 5 divided by 2 plus h. Okay. So in f of x, again, everywhere you see an x, plug in 2 plus h. All right, so there's f of 2 plus h minus f of 2. So that's just 2 over 5 minus 5 over 2. All divided by h. These problems, by the way, are a little harder than I'm going to make the exam, just so you know. This limit problem, if it comes up, will be a little easier to evaluate. So where should I go from here with this limit? The limit as h approaches 0. Well, I need to simplify stuff, right? So 2 plus h over 5, that's the same thing as 2 over 5 plus h over 5. Okay. And then minus 5. I can't do that here. This is, I can't do anything else other than 5 over 2 plus h. This is not the same thing as 5 over 2 plus 5 over h. Okay? And then minus 2 over 5 plus 5 over 2, all divided by h. Okay. Yes, and then someone online said we're going to need to get a common denominator, and that's exactly right. First, I'm going to cancel out this 2 over 5 with this minus 2 over 5. And then this is going to become the limit as h approaches 0 of h over 5 minus 5 over 2 plus h plus 5 over 2, all divided by h. So I don't want a common denominator for all three of these things. From here, what I want to do is I want to remember that when I'm taking the derivative of a sum, that's the sum of the derivatives. So it's going to go a lot nicer for me if I break this up into the limit as h approaches 0 of h divided by 5, all divided by h, plus the limit as h approaches 0 of negative 5 over 2 plus h plus 5 over 2 divided by h. So everybody sees that I just broke this up into that plus that. Okay. All right, what happens in this limit? Keep in mind that this is, exactly. This is just the limit as h approaches 0 of 1 over 5, which is just 1 over 5, right? Plus, now in this limit, I need to get a common denominator. And so the common denominator is just going to be, well, just multiply their denominators together, right? So I'm going to multiply top and bottom here by 2. I'm going to multiply top and bottom here by 2 plus h. Okay. So when I do that, I'm going to get negative 10 plus, well, this is going to be 10 plus 5h. Divided by 2 times 2 plus h. And then this h you can also write in this denominator, right? So then these cancel, minus 10 and plus 10. And then what else cancels? Perfect. Now the top is just 5 times h. The bottom is 2 times 2 plus h times h. So I can cancel that h from the top and bottom. Only after I cancel the minus 10 with the plus 10, because those didn't have h's. Okay. And so we're left with, well, this limit is just 1/5 plus this limit here, I'm going to get 5 over, I can just plug in 0 into this now, right? And there's no issue. So I should just plug in h equals 0. Yeah.
Yeah, how'd you get, so when you did, cancel out those H's?
Yeah.
There was 5H, and how'd you, was it because you would have been 2H?
Yeah, exactly. Because there was an h here. Let me subtract, get rid of these. So once I canceled the minus 10 with the plus 10, the top just looks like 5h over 2 times 2 plus h times h, right?
Or that H on the outside?
Just from distributing up here. So this is minus 10 plus 10 plus 5h. Yeah. Yeah, and then those h's cancel. And so here in this limit, I'm going to be left with, now I can just plug in h equals 0, and I get 5 over 4, which is exactly what, from the power rule, what we expected, right? 1 over 5 plus 5 over 4. And then you can get a common denominator of 20 here if you want. So multiply top and bottom here by 4, top and bottom here by 5, and you'll get 4 plus 25 is 29 over 20. Okay. Questions on that? All right. So exam problem 2, analytic limits. So let's look really quick at part 1. So the limit as t approaches 3 of 1 over t minus 3 squared. So what's the first thing you should try to do? Yeah, just try to plug it in, and what happens when you do that? Yeah, it's undefined, and so what did we say happened when we get something like 1 over 0? It does not exist. In my instructions, if the limit is infinite, indicate this in your answer. So D and E would get you partial credit here, but we can say a little bit more. So the bottom 1 divided by 0 usually means one of 3 things is happening. We're either blowing up like this, we're either blowing up like this, or we're either doing something like, I guess you could also have, they both go negative. But which of these 3 cases is happening here? As we approach 3, remembers what we did with something like this. The top is always positive, right? What about the bottom? Yeah, the bottom's always positive except at t equals 3, but the bottom's always bigger than or equal to 0. So in this limit, I'm looking at something that's blowing up. I'm trying to divide by 0, so that's blowing up. And everywhere but t equals 3, this thing is positive. So what do we think is happening in this limit here then? Am I getting plus infinity, minus infinity, or maybe some weird combination of the two? Plus infinity, right? So I'm gonna get that this is equal to plus infinity. Okay. So remember, we spent a day on vertical asymptotes. When you try to plug in a number and you get some constant divided by 0, that means that the limit doesn't exist, first of all, but it could be blowing up to positive infinity or negative infinity. Okay. So the other 2 will pick up from there on Thursday. Okay. So this first one, by the way, I would probably only give you a linear function for time. I do recognize this practice exam is going to take you longer than an hour, okay? I'm gonna whittle it down. So don't worry about that this one seemed a little longer than it should have.
How would you do if it's like when you said